Hello, good day, and welcome to this 6G Talks by 6G Flagship at the University of Oulu. My name is Nurul Huda Mahmood. I'm a coordinator for the Wireless Connectivity Research Area in 6G Flagship, and today I'm going to talk about Resilient by Design, a resilience framework for industrial communication networks. So before delving deeper into the talk, this is the outline of the talk. So first I will give an introduction on 6G, and then I will talk about industrial wireless communications, and then we'll go to the main topic of this talk, that is resilience, explaining what is resilience, why is it needed, and how can we ensure resilience in wireless industrial networks. So, what will 6G be? We have all seen this or similar figures many times before. This shows the evaluation of a wireless network from the 1G to the 5G. If we look at this trend a bit deeper, we can see that there is a trend that combines two generations. So if you look at 1G and 2G, you will see that 1G introduced mobile communication, while 2G established it, made it widespread. We know that GSM has been one of the most popular and very successful wireless communication systems, right? A similar trend is observed with 3G and 4G. So when you look at 3G and 4G, you will see that 3G introduced mobile internet, but it was very slow at the time of 3G, and it was also very expensive. With 4G, mobile internet became established, and it became very widespread, and almost everyone now uses mobile internet in their phones. What kind of trend do we see with 5G and 6G? Okay, so if you look into 5G, 5G is the first wireless technology or wireless system that introduced multi-service communication. If you look at 1 to up to 4G, we can see that the trend was basically focused on mobile broadband, and it was a consumer market driven. So basically, from 1G to 4G, the wireless system tried to provide wireless connectivity to the end user, to a normal consumer user, right? But with 5G, multi-service communication was introduced. So 5G is the first wireless system which introduced three different service classes, namely enhanced mobile broadband, which is an extension of the mobile broadband we saw up to 4G. But then two new service classes were also introduced, namely massive IoT or massive mobile type communications and ultra-reliable low-latency communications. Okay. So 5G, we can say that introduced the concept of multi-service communication. Hopefully in 6G, what will happen is that if you look at the same trend as 1G and 2G, 3G and 4G, so hopefully in 6G, this multi-service communication will be established and it will become widespread. So that's basically our feeling or our forecast into what 6G will be in terms of the application area. Now, if you look at the timeline, so whenever generation is rolled out, there's a life cycle of about 10 years into the making. So we can see that first a generation starts with academic research, and then it goes into specification by ITU, and then it goes into standardization, for example, by 3GPP and other standardization bodies, and finally the product rolls out, right? And in this first phase, there are also usually EU flagship projects, which are like larger scale projects within the EU, which tries to research these generations. So with 6G, we can see that the academic research in 6G started actually right here in 6G flagship in 2018. That's even when we did not have 5G. And then in 2023, now about 2 years ago, a draft specification of IMT 2030, which will define what 6G will be, was released. Okay. And also we have seen that EU flagship projects HEXA-X and HEXA-X2 was running from 2021 to 2025. And then last year in 2025, also the standardization process for 6G kicked off in March, and then hopefully towards 2030 we'll have the first 6G product rolled out. This is another timeline, but I will not go into the details of this timeline. This just shows the evaluation of different steps leading to commercial 6G deployment, hopefully sometimes in 2030 or 2029. So we have seen that now we are in the phase of researching and moving from research to defining what 6G will be. So to understand what 6G will be, we first need to look into its drivers. So what are the goals, trends, and opportunities of 6G, considering various aspects such as its motivation and societal consideration, user and application trends, network technology trends, and spectrum implication? So we can drive these drivers of 6G into three aspects, or three, let's say, different classes. So the first are the societal goals. What does the society expect from 6G? The second are the market expectations. So what are the market drivers that are driving 6G? And finally, what are the operational necessities or operational needs of 6G? So for the societal goals, 6G will be designed to support various diverse goals such as inclusivity, ubiquitous connectivity, sustainability, innovation, enhanced security and resilience, and so on. These goals can be distilled into three aspects. The first is bridging the digital divide. Basically, with ubiquitous connectivity, 6G should ensure that everyone has inclusive access to the wireless network that is needed to support essential services. This means connecting the unconnected in, for example, rural areas or the underdeveloped world. The second aspect is the sustainable development. Basically, 6G is envisioned as a green network, so 6G should play a pivotal role in reducing carbon emission, improve energy efficiency, and enhance the social governance efficiency. Here, we should note that by sustainability, we do not only imply environmental sustainability, rather, sustainability has three aspects, namely social, economical, and environmental. And sustainable development of 6G should incorporate all these three aspects of sustainability. The last of these societal goals that is driving 6G is the development of the digital economy. 6G should catalyze the emergence of new immersive applications, usage scenarios, and a pervasive information infrastructure under a secure and resilient framework that will result in economic benefits for the society as a whole. So basically, 6G should not only be a new generation of wireless technology, but it should be a driver for economic growth. So we have seen what are the societal goals that is driving 6G. Now let's look at what are the market goals that is driving 6G. So in terms of user trends, 6G will affirm the trend set in 5G towards incorporating reliability, latency, and efficiency in the quality of service consideration. This is basically saying that, as we said before, 5G introduced these three different service classes, and 6G will continue to support these three different service classes. So 6G will continue the move towards multi-service communication. The goal is to enable by support novel capabilities and new services that can provide the needed network connectivity. So there are many different user and application trends that has been identified for 6G. Here we highlight three of them. The first is smart cities, which leverage multidimensional sensing capabilities to monitor and manage diverse sensor data to enhance the services in a city, for example, enhancing risk prevention, enhancing service delivery, and enhancing the resource optimization of the city. Second is industrial production, and we have seen in 5G this emergence of service class URLLC, which is mainly targeted towards this industrial automation or industrial communication. And industrial production here empowers industrial IoT networks to improve manufacturing efficiency through real-time data, cyber-physical systems, and human-machine collaboration. Later in this talk, we will highlight more on this industrial communication part of 6G. The third aspect is the daily life enhancement. That means elevating daily life experiences through personalized digital healthcare, smart homes, and high bandwidth immersive smart education or immersive entertainment. So we have so far talked about the societal goals and market expectations that are driving 6G. So the drivers of 6G, these two aspects. Now let's see how these two drivers translate into operational needs. That means what should 6G deliver to meet these two expectations? 6G technology design need to prioritize operational necessities, reflecting the need to manage complexity, drive efficiency, and reduce cost. So basically, 6G networks should not be super complex. should be highly efficient and at the same time should be cost effective. This can be achieved by supporting end-to-end visibility and automation and advanced spectrum and energy efficiency procedures. So for example, just to cite a few examples, so for example, 6G will include new high-frequency bands, for example, communication in the sub-terahertz bands, which can support new applications such as immersive communication. Also, other technological enablers of 6G can be, for example, extreme MIMO, that means very large number of MIMOs, reconfigurable intelligent surfaces, non-orthogonal multiple access, and combined systems such as joint communication and sensing. So as mentioned earlier, that ITU released the first draft of IMT 2030, which will basically define what 6G will be, and this was done in November 2023. Now let us look a little bit into how these above 6G drivers that we discussed are reflected in this framework released by ITU, or this IMT 2030 framework. So this IMT 2030 framework outlines 4 different usage scenarios or 4 different drivers for 6G. These are sustainability, connecting the unconnected, security and resilience, and ubiquitous intelligence. So basically these 4 overarching drivers of 6G will drive the design of 6G network. Okay. Then it goes on to define 6 usage scenarios of IMT 2030. And you can see here that the usage scenarios in green, these are the ones that are extension of the usage scenarios that we talked about earlier that were introduced in 5G. So mainly expanding eMBB, MMTC, and URLLC into 6G usage scenarios of immersive communication, massive communication, and hyper-reliable and low-latency communication, respectively. Alongside, 3 new usage scenarios are also introduced that reflect the new drivers and new, let's say, operating conditions of 6G. These are integrated sensing and communication, or ISAC, AI and communication, and ubiquitous connectivity. So we have seen the usage scenarios or the drivers of 6G, and now in this IMT 2030 document, what are the capabilities of 6G? So in terms of the capabilities, the operational needs of 6G, they have outlined many different, let's say, capabilities of 6G. And here also we have 2 colors, the green and the blue. The greens are the ones that are enhanced capabilities of IMT 2020. So they are basically the extension of 5G that goes into 6G with higher numbers or higher or lower, more stringent requirements. Alongside, there are also new capabilities of IMT 2030, which are not categorized in terms of numbers, but which are more like capabilities in terms of qualities. So for example, sustainability, applicable AI-related capabilities, sensing-related capabilities, positioning, and so on and so forth. So with all these different capabilities, they define what are the operational needs of 6G. Here we can highlight that not all of these capabilities will be needed at one shot. So for example, some service classes or some usage scenarios will require a set of these capabilities, while another usage scenario will require a different set of these capabilities. So far we have focused on the general 6G, what 6G will be in general. In the second half of this talk, so the rest of this talk, I'm going to focus on the industrial communication, which is going to be one of the main usage scenarios of 6G. You may recall that industrial production development is one of the key market drivers of 6G that we talked about earlier. So basically, industrial communication networks are communication networks that connect the different elements in an industrial production floor. When we're talking about industry, we should talk about Industry 4.0, which refers to the fourth industrial revolution, characterized by the integration of Internet of Things, or IoT, artificial intelligence, and big data into manufacturing and industrial processes to create smart factories. Industry 4.0 is aimed at real-time decision-making, enhancing the productivity and making the production cycle flexible and agile to ultimately support a lot size 1 manufacturing. That means to ultimately support such flexible operation that you can produce 1 unit of certain product. Okay. And one of the main enablers of Industry 4.0 is sensors, because basically to enable this real-time decision making, to enable this enhanced productivity And to enable this flexible and agile operation, you need to deploy a lot of sensors that collect real-time data and also some central node which can process this data to make smart decisions. And at the backbone or underlying all these sensors is the industrial communication network, or the network that connects all these sensors to the central node and that allows these sensors to send the data to the central node so that the vision of Industry 4.0 can be realized. So what is industrial communication network and what are the needs of communication network in an Industry 4.0? As we said before, just to repeat, industrial communication network is a set of the sensors that connect to a control network, right? And there are two aspects of this industrial network. So first is the OT, operational technology, and the second is the IT or information technology. So basically at the lower end of this network, you have all these devices such as sensors, PLCs or programmable logic controllers, AGVs or automatic guided vehicles and so on, which are sensing different information and also which are doing different actions in the production floor. And then at the top level, in the IT level, all this information is connected into enterprise resource planning or lifecycle management and so on. Right? So what are the requirements or KPIs of industrial communication network? So basically to support this vision of Industry 4.0, industrial communication network should be highly reliable, should have very low latency and low jitter, should be well synchronized in time so that there is a common sense of the time, should support diverse quality of service requirements to meet the diverse needs of different operational needs in the factory, and also should support network availability. That means the network should be highly available so that there is no downtime or there is very limited downtime. So how are industrial communication networks realized? Traditionally, or when, let's say, first this industrial communication network was introduced, Fieldbus was the main protocol that supported industrial communication network. So it used to be implemented using Fieldbus protocols, but they were not very reliable. As time progressed, then Ethernet-based industrial communication networks or industrial communication protocols were introduced, namely, for example, Profinet, which is one of the most common protocol, which utilizes TSN or time-sensitive network to improve real-time capabilities. So Profinet is a real-time Ethernet solution for industrial automation that uses transparent clock mechanism and bandwidth reservation to support real-time and isochronous real-time connectivity. So that means very high precision, very high reliable, very low latency communication. Okay. So as we said, Profinet uses TSN to realize or to materialize this high reliability and low latency. So what is TSN? Basically, TSN is a set of IEEE 802 protocols that allows the traffic to be controlled in such a way that you can ensure high reliability and low latency. TSN features include a central network controller that manages resources by configuring network devices for optimal data transmission. For example, it can reserve a certain bandwidth for critical or high priority traffic to ensure that those data streams receive the necessary resources that are needed. Okay. Then also there is traffic shaping. That means traffic can have different priority classes, with higher priority classes given higher priority in the transmission. Then you also have time synchronization in TSN, which means that the whole network has a unified understanding of the time so that very low jitter applications can be supported. And finally, the reliability features of TSN include, for example, frame replication and elimination for reliability, which says that a packet is duplicated multiple times and transmitted over different parts of the network at the transmission side, and then at the receiver side, then whichever packet is received earlier is taken, and then the other packets are eliminated or discarded. Okay. In this way, you can ensure high reliability and you can ensure that any network disturbances can be overcome because the packet is replicated through different parts of the network. So far we have seen into, let's say, what are the different protocols of industrial communication network. We have said that first it was Fieldbus, then it moved to Ethernet, which can support isochronous real-time communication. That means very high reliability, low latency, deterministic communication. But so far, Ethernet-based solutions were like wired solution, And one of the main drawbacks of this solution is that they limit flexibility, scalability, and deployment options, because you know that it's not very flexible to have wired connections. And also it incurs a high operational cost because of these cabling needs and maintenance needs. So wireless technologies, for example, such as wireless LAN, Zigbee, and Bluetooth-based technologies, such as VISA and wireless HART, have also been used to support industrial communication network. As you can see from this plot here, of course, currently it's not widespread, so it's only 8% of the overall, let's say, industrial communication network. But this is a growing sector of industrial communication network because of its flexibility and because of the, let's say, benefits that it can provide. However, these technologies, since they are still quite new in terms of industrial communication, they cannot support very high reliability. Mainly, for example, you know that wireless LAN operates in the unlicensed bandwidth, so this interference from other users in the unlicensed bandwidth. So one trend to support this wireless communication in industries is the URLLC, or Ultra Reliable Low Latency Communications Service class, that was introduced in 5G. So this is a first step towards having a unified wireless connectivity solution for IoT requirements. And that we can see from this figure, which we are repeating, that you see industrial and vehicular automation is one of the main use cases of URLLC in 5G. However, we have to say that URLLC, as introduced in 5G, had some limitations. So, for example, it had limited KPIs because URLLC only defines reliability and low latency as the main KPIs, whereas we have seen before that in industrial communication you also need other KPIs such as availability or low jitter, accurate synchronization, and so on. Another limitation of URLLC is that it is application agnostic. That means basically you have a one-size-fits-all solution, whereas in industrial communication networks you need to have different solutions for different applications. The other aspect of URLLC as defined in 5G is that it only focuses on single link, whereas in industrial communication networks you may need to support end-to-end communication over multiple links. So end-to-end perspective is missing in URLLC. As such, it is not very scalable. So to support these needs of industrial communications in 6G, we have said earlier that there's this hyper-reliable and low-latency communication service class. And we believe that the limitations of URLLC will be supported in this usage scenario by incorporating resilience features into hyper-reliable and low-latency communications. So what do you mean by resilience features? We are going to highlight more about this in the next slides. But to summarize, we can say that resilience features means that the communication network should be application aware, and it should try to deliver the service that is needed according to the application. If an application requires very high reliability, but maybe not so much low latency, then it should be able to adjust according to that application. Okay. Secondly, it should support novel KPIs, such as, for example, availability. It should also be scalable, so that it does not focus only on one link, but it can support this end-to-end perspective. And finally, it should be secure by design because, as you know, security is one of the main quality of service requirement in industrial communication networks because security is important for many aspects. So now let us try to look a bit deeper into what is resilience, what is it, and why is it needed. Resilience is defined as the ability of a network or a system to continue operating correctly during and after a natural or man-made disturbance. So here we should note that this natural or man-made disturbance, that means interruption or disruptions of the network that are unknown or unexpected. Resilience mainly includes two aspects. First, maintaining the quality of service in the face of disruption. That means continuing to operate or at least trying to continue to provide the service in the face of disruption. And the second thing is the quality of remediation or recovery from a failure. That means how well you recover from a failure. There are two other terms that are often mistakenly used synonymously with resilience. These are reliability and robustness. And here we should highlight what are the differences. As you can see from this figure, resilience is much broader than reliability and robustness, and it incorporates both of these aspects. So reliability is the ability of a network or a system to perform as required for a given time interval under a given conditions. That means under certain given scenario, the network should operate as it is expected to operate. On the other hand, robustness is defined as the ability to continue operation in the face of known challenges. So basically, if you expect that certain kind of disruptions may happen, then you make your network robust against those kind of expected disruptions. So why is resilience gaining importance? Because of multiple factors. We may highlight here that resilient by design has been designated as one of the common design principles of 6G and beyond by some like-minded countries. So it is high on the agenda of 6G design. Why? Because systems are becoming more and more complex day by day. Networks are becoming much more integrated, and that means the cost of failure will be much higher as systems become more complex. Secondly, increasing unpredictability, and this includes natural and also man-made unpredictability. From the natural side, we know that the weather situation is becoming worse and worse every day. We have adverse weather conditions. We have also extreme events like floods or cyclones, which affect the network. From the man-made side, we have, for example, increased geopolitical tensions and advanced security threats, for example, those induced by AI and so on. So this kind of unpredictability requires that we make the network robust or resilient against such unpredictable disruptions. Then there's also technological interdependence. Because of these globally connected networks, one technology depends on another one. And then finally, there's a shifting paradigm from prevention to adaptation. So basically, in order to ensure or enhance efficiency, networks are becoming much more adaptable, agile, and they're basically trying to be built so that it can adapt to the changing conditions instead of being fail-proof, because you know that making networks or making systems fail-proof is quite costly. So now in this, let's say, last 10 minutes, let us look into how resilience can be ensured in the network. So how to ensure resilience? So of course, there's no one solution to this question of how to make networks resilient by design. But here we'll propose one framework that we have been researching here in 6G Flagship, and that was presented in this paper. You can see the link here, which basically says that instead of making networks best effort, we should make networks resilient by design by incorporating this 4P framework. So basically, networks should have these stages of prediction, preemption, protection, and progression. So let's look into them one by one. First is prediction. So prediction means that advanced monitoring and predictive capabilities should be incorporated into the network to predict or detect faults. Here we can have two different approaches. So for example, we can have model-based approaches where we can use Bayesian framework for prediction, or context awareness through multimodal data fusion to predict what will be the network state in the future, or to predict when failures may happen. The other option can be to use data-driven AI methods, for example, using machine learning techniques such as supervised learning, unsupervised learning, or reinforcement learning. So basically using data-driven approaches or using data to predict the network evaluation ahead of time. And also we can use other approaches such as time series methods, for example, long short-term memory, or graph-based approaches. Then finally, we can also use advanced techniques such as digital twin integration. So basically using the digital twins of the network to predict the network behavior over time. So with this prediction part, the goal is to predict when failures may happen. Once you have predicted when the failure happens, next we need to take preemptive actions or proactive actions so that we can prevent these failures even before they happen. So the second part of this resilient by design framework is the preemption part, where you try to prevent a predicted failure from happening. This can be done, for example, by proactive resource management. So allocating resources to ensure that, for example, there is no outage, or efficient traffic flow multiplexing. So for example, to reroute the traffic to avoid a node that is predicted to fail. And then also we can have security preemptive measures such as predictive analytics for threat mitigation or zero trust architecture that incorporates continuous authentication and authorization for all devices so that the security failures can be prevented or proactively prevented. The third part of this framework is the protection part. So even though no matter how hard we try or how well we design our network, failures are bound to happen, right? As we said, we are moving from making networks fail-proof to make networks adaptable. So once a failure happens, the system should try to protect the network from the impact of this failure and also try to overcome this failure as quickly as possible. So here we can do this, for example, by isolation mechanisms. That means if a part of the network fails, then the network should try to isolate this network so that the failure does not propagate. The second option can be, for example, differentiated services. So having different service levels. So you can have a full service, but you can also have, for example, reduced service or even basic service, so that in case there is a failure, the network still continues to operate, albeit at a lower service level. Okay. The third is this traffic engineering strategies. So for example, when you have a failure, then you should try to prioritize critical and delay sensitive services or critical and delay sensitive traffic, while, for example, blocking the low priority traffic or low priority services, so that at least the important and mission critical services can be continued to be supported. And finally, we can have diverse network architecture, so alternative networks, for example, space, air, and ground integrated networks that integrate terrestrial and non-terrestrial networks to support adaptive network architecture. The final part is progression. So basically this is outer loop of this resilient by design framework, which tries to continuously update the other three steps, namely prediction, preemption, and protection, by learning from the experience that the network goes through regularly. So basically it's a continuous learning cycle. And here we can have, for example, dynamic model updates. So if you are using AI models, these models can be updated based on the information or based on the experience. Secondly, you can also adopt new tools. So for example, if some tools need to be replaced, then you can have data-driven refinement. So basically integrating new observations into the data so that you have a much more richer data source. And then also applying transfer learning techniques. So for example, system that was learned in one aspect can be transferred to another scenario so that we don't need to learn from scratch in a new scenario. And finally, there should be a holistic performance assessment that is basically continuously monitoring how this resilient by design framework is working or how it's performing in terms of the KPIs, in terms of the cost performance trade-off, and also in terms of the security requirements. So with that, I want to conclude this talk. So in this talk, first of all, we talked about what 6G will be. So we gave basically an overall introduction of what 6G will be. Then we focused into industrial communication network, which is one usage scenarios, maybe one of the most important usage scenarios in 6G. And we said what are the requirements of industrial communication network, how URLLC was introduced in 5G to support industrial communication networks, what were the limitations of URLLC, and how can we then address these limitations in 6G. Then we went on to say that resilience would be one of the, let's say, main design focus in 6G that will address the limitations of URLLC. And then we highlighted what is resilience, why is it needed, and then we proposed one framework to support resilient by design networks or to incorporate resilience in the network design. Okay. And finally, we'd like to remark that resilience is a cross-disciplinary topic that requires interdisciplinary collaboration. It's a very wide topic that needs inputs from different fields to make this happen in an efficient way. With that, thank you very much for attention. I would also invite you to look into the other talks in this 6G Talks series by 6G Flagship. Thank you.